This video is going to discuss formal charges and resonance structures. Sometimes a Lewis structure can be correctly drawn two different ways. For example, we drew carbon dioxide like this, with a double bond on each side of the carbon. You could also draw carbon dioxide like this, where you have a single bond on one side and a triple bond on the other side. This still meets all of the requirements. It's got the correct number of electrons drawn, and each one of the atoms has a complete octet. This oxygen has 2, 4, 6, 8, carbon has 2, 4, 6, 8, and this oxygen has 2, 4, 6, 8. So these are both Lewis structures that are correctly drawn. We have a system that will help us to evaluate these two Lewis structures and determine which one is more likely to be correct. It's called formal charges. The formal charge is the charge that an atom would have if all of the electrons in a covalent bond were shared equally. Here's how you calculate a formal charge. You look at each atom, you take the number of valence electrons, and you subtract the number of electrons that you've drawn. So for this oxygen, the number of valence electrons is 6. I get that off of the periodic table. Then we have drawn 1, 2, 3, 4 non-bonding electrons, and each one of these bonds gets split in half. Each bond is donating 1 electron to each of the atoms it touches when you do formal charges. So that's why it's drawn like this. They've actually divided the bonds in half. So right now oxygen has 1, 2, 3, 4, 5, 6. You take your valence electrons, subtract what you've drawn. This oxygen has a formal charge of 0. For carbon, carbon has 4 valence electrons. Cut these bonds in half. We've drawn 1, 2, 3, 4. 4 minus 4 is 0, has a formal charge of 0. Same thing for this oxygen. It's identical to that one. On the right-hand side, this other structure, the number of valence electrons is the same for the atoms. What changes is what we have drawn. This oxygen, when you split that bond in half, has 2, 4, 6, 7. And 6 minus 7 gives you a formal charge of -1. Carbon still has 4, but this oxygen has 1, 2, 3, 4, 5. 6 minus 5 is +1. Ideally, all of your formal charges would be 0. So this is the more correct Lewis structure because all of the formal charges are 0. Here is another example. This is a molecule that can be drawn 3 different ways. You could have a double bond on each side, or a single bond and a triple bond, but then you have to decide if the triple bond should be between the carbon and the sulfur or between the carbon and the nitrogen. So we're going to use formal charges to determine that. Ideally, we would pick the one where the formal charges are the closest to 0. Well, that knocks this one out, but leaves these two as options. So the second thing that you look at, if there's a negative charge, the negative charge should be on the more electronegative atom. So the atom that's the closest to fluorine on the periodic table. Nitrogen is more electronegative than sulfur. So nitrogen should have the negative charge. This is the most correct Lewis structure for this molecule. Next, we're going to talk about something called resonance structures. A good example of this comes from the molecule for ozone, which is 3 oxygens bonded together. This particular Lewis structure is showing you the angle between the bonds. The way we would have drawn it looks like this. Now, ozone is going to have 1 double bond somewhere. But how do you know if the double bond is here or if the double bond is here? Scientists have studied the length of these 2 bonds and found that they're exactly the same. A double bond should be shorter than a single bond. So the fact that they're equal in length indicates that something else is going on. When you have a case like this, where two structures are basically the same but not exactly the same, we call them resonance structures. What you would do is draw both of the structures and put a double-sided arrow in between them to indicate that they are in resonance with one another. What we're saying is that what is going on is some combination of these two structures. When scientists studied this molecule and looked at the electron density, these two bonds are basically equal, even though when we draw our Lewis structures, one of them needs to be single and one of them needs to be double. So it's almost like instead of having a single and a double, you've got 1.5 here and 1.5 here. One final thing that I want to point out is that in order to have resonance, you must have structures that are equivalent to one another. Earlier in the video, we evaluated these three structures for which one was the most appropriate. This is not a resonance situation, and the reason for that, even though we're looking at different positions for a bond, this would be between a carbon and a nitrogen, this would be between a carbon and a sulfur. They are not equivalent to one another. So in order to have resonance, if you're moving a bond around, it needs to be between atoms that are the same element. If you have a case like this, where they're not equivalent to one another, you should be able to use your formal charges to pick which one's the most appropriate. If you have a case where they're all equivalent to one another, you can draw multiple structures and put the double-sided arrow to indicate that they are in resonance with one another.